This section is the next part of that initial derivative at a point. And we're going to be talking about velocity and the rates of change. So it's very much the same as what we saw, but it's more of an application now instead of learning the concepts. So learning outcomes: describe the velocity as a rate of change, explain the difference between average velocity and instantaneous velocity, and estimate the derivative from a table of values. So we have this formula here. The average velocity is s of t minus s of a over t minus a, and that's much like that secant line, the derivative or the slope of a secant line. And so I'm hoping you see that similarity there. Now the instantaneous velocity, though, is the velocity at a single point instead of over two data points. So our velocity is the derivative of the position function, which the limit as t approaches a, of s of t minus s of a over t minus a. So much like we saw before, we could do it through the secant line, those 2 points, and get the average velocity. But look at that slope there compared to the slope of the tangent line. We would not be as close. The tangent line is going to be the instantaneous velocity. So for this problem, I left the table up on this just so we don't take the time to fill it in again. But a lead weight on a spring is oscillating up and down. Its position at time t with respect to a fixed horizontal line is given by s of t equals sine of t. Use a table of values to estimate v, the velocity at time 0. Check the estimate by using the definition of derivative. So we have, we're looking for the limit as time approaches 0 of s of t minus s of 0 over t minus 0. So that's going to be the limit as t approaches 0 of our s of t is sine t minus sine of 0 over t minus 0. Well, if you recall from your pre-calculus days, what is sine of 0? That's just 0. So in essence, we have the limit as t approaches 0 of sine t over t. Now, we know what that is. I hope you recall from what we did in the looking at limits and looking at the table of values, or looking at a table like this. So I have my t's going from negative 0.1, negative 0.01, negative 0.001. So on the left side of the given value, and then on the right side as well, 0.1, 0.01, 0.001. And if you notice these values, they are of course symmetrical, but they are approaching what value? And I hope you're all yelling at the top of your voices, it's approaching 1. But you probably already knew that because back a few weeks ago, we did this where limit as t goes to 0, and we may have said x goes to 0 or theta goes to 0, but of sine t over t equals 1. That's what we did back before. So hopefully that rings a bell. So our velocity at time 0 is 1. I'm going to move on here. A rock is dropped from a height of 64 feet. Its height above ground at time t seconds later is given by s of t equals negative 16t plus 64, and the interval is from 0 to 2. I'll be honest, when I first did this problem, I was focusing on that 0 to 2, but the thing to focus on is what I underlined here. Find the instantaneous velocity at 1 second after it is being dropped. Use the definition of the derivative. So we're going to look for the limit as t approaches that 1 second mark of s of t minus s of 1 over t minus 1. So that's going to be the limit as t approaches 1 of negative 16t squared plus 64 minus, and I didn't calculate s of 1, but s of 1 is going to be negative 16 times 1 squared plus 64. So that's negative 16 plus 64. And I get 48 out of that. So minus the 48. All divided by t minus 1. So let's do some simplification here. We have the limit as t approaches 1 of negative 16t squared plus 16 over t minus 1. And that can factor to be the limit as t approaches 1 of negative 16 times t squared minus 1 over t minus 1. So you probably recognize now that we can write this as the limit as t approaches 1 of negative 16 times t minus 1 times t plus 1 over t minus 1. And what happens to those t minus 1s? Well, they divide out. And we have a limit as t approaches 1 of negative 16 times t plus 1, which will end up being negative 16 times 1 plus 1, which is negative 32. And this is in feet per second. Okay, hope that was fun. Moving right along. The instantaneous rate of change of a function f of x at value a is the derivative f prime at a. So, hope that makes sense. Homeowner sets the thermostat so that the temperature in the house begins to drop from 70 degrees at 9 p.m., reaches a low of 60 degrees during the night, and rises back to 70 degrees by 7 a.m. the next morning. Suppose that the temperature in the house is given by the function t of t is 0.4 t squared minus 4t plus 70. I was reading those temperatures. I'm like, wow, I keep mine at 68 in the day and 58 at night. So I'm 2 degrees lower. So this problem is asking, so it's at 9 p.m. is the time that starts. That's our time 0. And they want to know what's going to happen at midnight. So we're looking at t equals 3. And when I say this, it's little t equals 3. I know it can be confusing because you have a capital T of little t equals the 0.4 t squared minus 4t plus 70. So when doing the calculation, it's helpful to have our capital T of 3, which is going to be 0.4 times 3 squared minus 4 times 3 plus 70. And so the temperature at midnight would work out to be 61.6 degrees. So if we do our T prime at 3, the change of temperature at 3 hours into this is what I was talking about, that's midnight. That's going to be the limit as T approaches 3 of capital T of little t minus capital T of 3 all over T minus 3. So that's going to give us the limit as t approaches 3 of our 0.4 t squared minus 4t plus 70 minus the 61.6, because that's our little, or that's a big T of 3. So I should make sure that's a big T of 3 over t minus 3. We do a little bit of simplification here. And we have 0.4 t squared minus 4t plus, and it looks like that's going to be 8.4, I believe. Now, just double check my notes here. Over t minus 3. So if I were to factor out that 0.4, I get the limit as t approaches 3 of 0.4 times t squared minus 10t plus 21 over t minus 3. So I hope you see right now t minus 3 would be a factor of that. So the limit of t minus, as t goes to 3, of 0.4 times t minus 3 times t minus 7 all over t minus 3. So our t minus 3's will divide out. And we're left with the limit as t approaches 3 of 0.4 times t minus 7. Now we can plug the 3 in. We have 0.4 times 3 minus 7. That's going to be 0.4 times 4, negative 4. So that's negative 1.6 degrees per hour. Am I out of the space? And that's it. So that's the rate of change at midnight. It's going down by 1.6 degrees per hour. Okay, hopefully that helps. Moving on. Rate of change of profit. So they give this toy company can sell X electronic gaming systems at the price of this. The price of the gaming systems. P equals negative 0.01x plus $400 per gaming system. The cost of manufacturing X systems. So that's the price for one system to manufacture. That's the price to sell one. To manufacture them is going to be C of X. The cost is 100 times X plus $10,000. Find the rate of change of profit when 10,000 games are produced. So here we go. A couple things to be aware of. To get the profit, well, I need to come up with revenue. R of X. And that's going to be the price times how many are made. So P times X. So it's negative 0.01x plus 400. All that times X. So the revenue is negative 0.01x squared plus 400x. I guess I didn't need those parentheses at the end, but they have them. So our profit will be capital P of X, and that's the revenue minus the cost. So P of X will be that negative 0.01x squared plus 400x minus 100x. I run out of space over here. Plus 10,000. So our P of X would be negative 0.01x squared. 400 minus 100 is plus 300x, then minus the 10,000. Now, if we want to look at the change in profit at 10,000 units, that's going to be the limit as X approaches 10,000 of our P of X minus P of 10,000 divided by X minus 10,000. So, by the way, our P of 10,000 is going to be, I just plugged in the calculator, I got 1,990,000. So it looks like 1,990,000. So this works out to be, again, we're subtracting this, the limit as X goes to 10,000. Make this a little bigger. Of negative 0.01x squared plus 300x minus 10,000 and then minus that 100 or 1,999,000. 1,990,000, that's what it is. All divided by x minus 10,000. Okay, let's keep going. So this is going to lead us to the limit as x approaches 10,000 of negative 0.01x squared plus 300x minus 200, or that's 2 million, minus 2 million over x minus 10,000. Now, it'd be helpful if you factored out that negative 0.01 from the beginning. And we'd have the limit as x approaches 10,000 of negative 0.01 times, then we have x squared, and then we have 300 divided by negative 0.01, so that'd be negative 3,000. Let me verify that. Another 0. And then we have plus, and then we have 2 million, negative 2 million, so that's going to be what? It's a lot of zeros. Is that 200 million? 1, 2, 3, 1, 2, 3, yeah. Plus 200 million. So it's 200, comma, then 0, 0, 0, comma, one more 0. That's all over x minus 10,000. So I'm pretty sure it's going to have to work out that x minus 10,000 is a factor, so negative 0.01 times, so it should be an x minus 10,000 as a factor. Let's see what the other one's going to be. X minus, I'm betting it's going to be like 4 to x plus, no, it's minus, so 20,000. Yep, my x minus 20,000 divided by x minus 10,000. Those divide out, and we're left with the limit as x approaches 10,000 of negative 0.01 times x minus 20,000. So if we plug that in, we end up with negative 0.01 times 10,000 minus 20,000. So it's going to be negative 0.01 times negative 10,000. And that's going to give us 100. Now that's a positive. So I guess the conclusion would be to keep making devices. Okay, let's keep going. Kind of out of space for the next one. I'll work on the lower part. We're going to talk about scones. A coffee shop determines that the daily profit on scones obtained by charging S dollars per scone is P of S equals negative 20S squared plus 150S minus 10. The coffee shop is currently charging $3.25 per scone. Find the change in price at $3.25. That is the rate of change of profit when the price is $3.25, and decide whether or not the coffee shop should consider raising or lowering its prices of scones. So let's go forward. Same process, the limit as s approaches 3.25 of p of s minus p of 3.25 over s minus 3.25. Now, our p of 3.25, if you put that in the calculator, you're going to come out with 266.25. So we have the limit as s approaches 3.25 of negative 20 s squared plus 150s, this is just the p of s function, minus 10 minus 266.25, all divided by s minus 3.25. And that'll simplify to be negative 20s squared plus 150s minus 276.25 over s minus 3.25. And if I factor out the numerator, I'm going to factor out the 20. We have the limit as s approaches 3.25 of negative 20 times, we have an s squared minus 7.55 plus, this is going to look really weird, it's 13.8125. And don't lose heart over this because it actually factors out. I know we don't usually factor with decimals like this, so this becomes the limit as s approaches 3.25. Remember, we have the s minus 3.25 in the denominator. We have that minus 20. Now, guess what? S minus 3.25 is a factor of the numerator, as is s minus 4.25. So the s minus 3.25's divide out. We have the limit as s approaches 3.25 of negative 20 times s minus 4.25. And we plug it in. We have negative 20 times 3.25 minus 4.25. That's negative 20 times negative 1, which is 20. So the idea is, yes, raise the price of scones. Okay. Now we have a multiple choice thing here. The function d of t describes the number of miles a person is from Disneyland t hours after they left their house. Select the correct interpretation of d prime of 5 equals negative 10. So what this is saying is the rate of change of the distance to Disneyland after 5 hours is negative 10. So the person's traveling 10 miles an hour towards it, so because the distance is decreasing after traveling for 5 hours. So let's see which is the right one. Person traveling 10 miles an hour toward Disneyland after traveling for 5 hours. So there's your answer. And that does it. I know there's some pages, but I actually got it put in the wrong place. There'll be another lesson for the next part. Okay. Hope this helped.